So Manpreet isn't here. Unfortunately, due to some technical difficulties with HR, we were not able to get the current speakers, so we're going to move on to the next one, and so we're right now on schedule. I'd like to present to you Amir for his next talk.
Hey everyone. Okay, so hopefully everyone's had a good lunch, a little bit of energy. My name is Amir, I'm a researcher, and today I'm going to be speaking to you about a set of vulnerabilities related to API authorization flaws. So it's a really specific subset of API vulnerabilities, but one that tends to be quite prevalent, and the impact can be pretty material. So the talk itself, we're going to start with some definitions just to get everyone on the same page, make sure we kind of are talking about the same types of vulnerabilities, and then I'm going to get into concrete examples. The goal for me is to make this as tangible for you as possible, so we're going to walk through several examples of these vulnerabilities, actual vulnerabilities that exist in the wild. 3 of them are things that I've come across in my research. 2 are very recently disclosed sets of these vulnerabilities in different web applications that are actually kind of fun to talk through. The hope is that hopefully it'll give you a sense of what these vulnerabilities look like, how they come to be in place, how they kind of come to existence. And also, we'll talk a little bit about the severity of these vulnerabilities. They range in kind of their impact on organizations. And then I think the most fun part of this talk, we'll actually try to put on our black hats for a second, pretend black hats, and think like a script kiddie. What would someone do if they wanted to identify and exploit these vulnerabilities? So I'll kind of give you some of the steps that a malicious actor who's not very sophisticated, but has basic skills, would use to actually find these vulnerabilities and try and exploit your products. Hopefully it'll give you some pictures into ways in which you might mitigate those vulnerabilities as well. And then we'll talk a little bit about new challenges, how people are using LLMs and other tools to be able to programmatically scale these types of attacks. And then finally, we'll talk about mitigations. Cool. Okay, so first set of definitions. When we talk about auth, often we're talking about 2 different things. One is authentication, the other is authorization. Authentication is the process by which you verify that you are who you say you are. So my name is Amir. I'm able to supply credentials that prove that I am Amir to some other entity. Authorization is the process by which you validate that you have the necessary permissions to execute the actions or get access to data, whatever it is that you're trying to attest to. You have those necessary permissions according to your profile. So what's tricky here is that authentication is technically a little bit of an easier problem to solve for. It's a binary decision that's adjudicated across your entire product. You are a user, and that user ID is either valid or invalid across the entire product stack that a person may be interacting with. So all of the features within the product will have the same ID associated with a particular user. However, authorization is a little bit more nuanced, and this is where things get hairy. Authorization can vary based on the product features, specific portals, all the different things that you might interact with. One user may have permissions to access some things and another user may not. And because of that nuance and logic, that's where you often get product implementation vulnerabilities where authorization is not correctly implemented, and so users get access to things that they otherwise should not. Hopefully that's clear. So really this talk is about how an authenticated user, someone with valid credentials, might be able to bypass authorization to get access to things that they otherwise should not be able to access. Okay, and when we talk about these vulnerabilities, they're actually quite prevalent among the OWASP top 10 2023 API vulnerabilities. We're going to specifically focus on 2, broken object level authorization and broken function level authorization vulnerabilities. Broken object level authorization vulnerabilities, often referred to as BOLA, relate to the manipulation of API call payloads, particularly in user identifiers or object identifiers, to access data that's associated with other types of users. We'll get into actual concrete examples that will be a little bit clearer. But you can kind of think of this as basically calling an API, and instead of supplying it with your actual ID, your true valid user ID, you supply with another user's ID and get access to their data. Broken function level authorization is a very similar type of vulnerability, but instead of manipulating object identifiers, you're manipulating functions. function identifier. So within your call parameters, you're trying to execute actions that you otherwise should not have access to. There's a whole bunch of other stuff within the OAuth top 10 API vulnerabilities that are actually relevant here as well. We might touch on a couple of them over the course of the examples that we'll talk through, but we'll focus on the first two. Okay, and why does this matter? Just in case this is helpful, when we're interacting with web apps, when we're interacting with SaaS products, we're effectively interacting with a very thin abstraction on top of a bunch of API calls to servers. And those API calls are being made to endpoints that are often intended just to be used by the front-end client. So whatever is the UI framework that the product has, pushed out to your client to interact with its servers. These API endpoints are not meant to be used by other developers. They're not SDKs effectively that are assumed to be interacted with by sophisticated external entities. They're really just restricted to use by the front-end client. And as a result of that, there's a lot of implicit trust when developers are developing or creating these types of endpoints, which can be abused. We'll kind of walk through it, but a really tangible example of this is when you log into the Twitter homepage, the client will make something like 220 different calls to different endpoints, and a lot of those calls will be to endpoints that are really just tracking telemetry stuff, basically tracking where you are, how the app is performing on your end, but some of those calls are actually what drive your experience with Twitter or X. So for example, there's a particular endpoint that's called, that endpoint is referred to as home timeline. And in the home timeline, you supply it with your user ID, your validated, authenticated credentials, and you get back a response that's a JSON object. That JSON response actually has everything that's supposed to populate your Twitter feed when you first load it for the first time. That endpoint itself kicks off a bunch of different microservices on the X servers that generate for you what are, based on who you follow, the tweets that are relevant to your profile, the ads that are relevant to you, what is the mix of media that's going to be pushed out to you in the first 20 tweets that are populated in your feed. That home timeline endpoint is not necessarily designed for use by other developers. It's really meant to be called just from your web client front end. But we're going to talk through examples of where this can be abused. Okay, talked a lot about abstract level definitions. Let's talk about our first concrete example. So this is an example of a vulnerability I came across in an electronic health record software product. EHRs are software used by physicians' practices that manage basically everything in the practice. All of their patient records, their clinical encounter data, their claim submissions to insurance companies and how much they get paid back. There's a ton of sensitive information here, especially related to patient health records and social security numbers, all the personal stuff that actually needs to be captured for the business operations of a physician's office. This particular EHR is used by something around 10,000 different physicians' practices, and in total encompasses about 15 million different patients' records across all of these physicians' practices. Now, what's really nice about this EHR is they've built in a lot of functionality that makes it easy to use for practice owners. So if you're a back office admin or you're a front desk receptionist at a practice, one of the things that's really nice is you have the ability to go into a patient's record and look up kind of all of the claims history that they've had with your practice. And there's a nice little button on that UI that you can click that's called print. When you click that print button, it kicks off a request to an endpoint that is a printer microservice. Effectively, what that microservice does is it takes a call payload. This is sort of a sanitized view of that call payload. But that call payload accepts a parameter called claim ID, and it looks up that claim ID in the database of the EHR. Every claim that matches that claim ID, it pulls back, and it puts it into a nice PDF template, sends that back to the client, and as a practice manager, you can kind of print that off, give it to the patient, or send it off to another physician that you're referring a patient to. It's kind of like a nice package of all the patient's claims history. Now, what's really difficult is that neither the printer microservice nor anywhere on the database end is there a validation to check whether that claim ID that's being supplied with that call payload is valid and related to the user who's requesting it. So I can be logged in as a practice manager of Dr. Smith's practice, but by manipulating this claim ID, I'm able to access claims for every other practice that is also using this software. What makes this particular vulnerability really pernicious is that claim ID is an incrementing integer. It's very predictable. So you can effectively start with a valid claim ID and just increment up, decrement down, and effectively collect the entire claims history of every patient who's ever been logged within one of these physicians' practices that uses this EHR. What's really important here to highlight is that this vulnerability impacts just one single microservice across this entire product stack. Everywhere else that I've at least interacted with this product, I haven't found a similar authorization vulnerability. So it can be a very meaningful, impactful vulnerability, but also scoped in a way that can be difficult to find in sort of passing scans. So we're going to move on to a different electronic health record system. I do a lot of work with different EHRs. This is a different piece of software used by about 7,000 practices across the US. It's a very well-liked EHR as well. One of the things that they make available is a portal where, as a physician, you can log in, you can go to the encounter histories for each patient, and be able to edit those encounter histories. So obviously, if I'm your doctor, I can log in and say, I performed XYZ services, these are the codes associated with them. If for some reason there was an erroneous record, I can actually delete that encounter from the practice's history. So it's a nice control for the physician who should have read-write access to their encounter history. Now, this particular EHR also makes this portal available to patients. It's really nice for a patient to be able to log in and access their encounter history as well. What's different is that here on this prior slide, you can kind of see this abstracted view of a modal. There's an edit and a delete button that's available to the physicians, but on the patient side, those two UI elements don't appear. Now, when a physician clicks on those UI elements, it kicks off a call to an endpoint that takes those function calls, whether it's a delete or an edit call, and it executes those actions. Now, just because patients don't have those UI elements available to them to click doesn't mean they can't execute those actions. A sophisticated patient who maybe has a little bit of knowledge about this EHR can actually use that same call syntax and execute those same actions by effectively just sending that request, authenticated with valid session tokens, to the same endpoint, and actually be able to edit their own record or delete their record. What's really difficult about this is because the EHR is designed to give that functionality access across all records associated with a physician's practice, it's not really designed to authorize whether or not the user has access to them, because they assume anybody who can click on those buttons is already authorized to edit and delete everything in the practice's history. Now, patients should not have that functionality available to them, but because there's no authorization validation, a patient can actually delete or edit other patients' records as well. So a sophisticated malicious actor could wreak havoc on a physician's practice by effectively just going in and deleting all of their encounter history and their claims data. And you can see kind of here, again, sanitized views of these call payloads. All you're doing is changing what is called this parameter admin action to update encounter or delete encounter or del encounter technically. So very sort of nuanced syntax that's specific to this product, but if you're aware of it, you can actually cause quite a bit of damage. Both of these are still unpatched, so unfortunately I can't give you more concrete examples of what these products are, but these are both EHRs that are independent of each other used across the US. Okay, we're going to talk about something a little bit less scary. This is a vulnerability related to unmitigated resource consumption. This is sort of one of the other OWASP top 10 vulnerabilities that's actually very common, particularly in products that have infinite scroll feeds. So on the left-hand side, you'll see a screen for a product called TGIS. TGIS is an expert network. It's one of these products where you can subscribe and request interviews with subject matter experts, and those calls get transcribed and entered into a library. Now, what's really nice is if you subscribe to TGIS, I think it costs something like $10,000 or $20,000 per license. You get infinite access to this entire transcript library. Everyone's phone calls that have been ever conducted, you kind of are able to read those transcripts. Super valuable database if you kind of want to get up to speed on a lot of different domains. It's a really interesting, rich data resource. Now, what's interesting is when you log into TGIS, they'll actually kind of have a feed that loads the top 20 latest transcripts for you, basically, so you can click through them really quickly and see if there's anything interesting that's been logged recently. Now, the call payload that's made in order to populate that feed has a hard-coded parameter in for returning 20 records, the latest 20 records. What's interesting is, if you wanted to sort of request more data, you could actually just edit that. You could say, return to me 2,000 records, return to me 20,000 records. And as long as the microservice that was generating that data did not fall over, you'd actually get a giant amount of data back in that one call. What makes this really material for a business like Tigis is that you could actually download basically their entire transcript library in a matter of a couple of API queries and host that database elsewhere and no longer subscribe to their product. And you could do this with a trial license without ever having given them a credit card for that, $10,000, $20,000 subscription. The assumption on Tigis' part is that no user is going to be able to read through the entire transcript library with a trial license, but obviously a malicious actor executing a bunch of these calls could very efficiently just extract everything without having a significant footprint on their resources. This has obviously been patched, doesn't exist anymore, but it kind of gives you a sense of where it might occur. Whenever you see these types of sort of infinite scroll feeds, you can often find within the call payloads hard-coded parameter for how much data they're returning, and sometimes they're not validated, so you can actually edit that and return more data. It could also effectively cause a denial of service vulnerability if you request so much data that the microservice itself becomes overwhelmed. Okay, we're going to talk about something, maybe the scariest example that I have for you all. This was a vulnerability discovered in Field, which is a dating app, and it was discovered by a UK-based research firm called Forbridge. Field is a dating app that is kind of a view of what the world would look like if authorization was never implemented. Just kind of a fun idea to think about. What it meant is that when you're interacting with the Field app, your client device would make a bunch of calls to their endpoints. So for example, when you went into your own photo library, this is a dating app, you upload a bunch of photos of yourself. If you wanted to kind of go into your photo library and edit your photos or see what photos you've uploaded so far, the client would make a call to an endpoint with your user ID in it. What's interesting is you could actually edit that user ID and return back the photos of other users that were also using Field. And these are private photos. And my favorite example of all the vulnerabilities is that they had a specific endpoint where if you wanted to send a message to another user, the call payload was basically from user ID to user ID message. And you could actually edit those fields, so from another person's user ID to another user message would actually get executed as well. So you could effectively send messages on behalf of other users without them even knowing that you're logged in, because you actually don't have their password or anything. You're not authenticated as that user, but you're able to act on their behalf because of this authorization vulnerability. So the app itself was effectively a total free-for-all. If you were aware and sophisticated, you could effectively just go through everyone's messages, go and act as them. And after reporting this vulnerability, Forbridge said it took Field about 6 months for it to be patched. So it also gives you a sense, despite the urgency associated with this, actually going back and implementing authorization into a product, given all of the unique business logic for every single function, it can take quite a bit of time for these types of issues to be resolved. Okay. I know I called that one my favorite example, but this one is a really special one as well, for a different reason. This is an authorization vulnerability that gives you a view into the possibility of remote code execution. It's very unlikely that authorization vulnerabilities cause remote code execution. So this is kind of a special example as a result. And it's found within a product called Arc. Some of you may be familiar with Arc. Arc is a new browser developed by the browser company. It's a startup based in New York. And Arc kind of was invented, kind of developed with the intention of changing the user interface for the internet. So kind of creating new ways in which users might be able to customize their web experience in total. And one of the ways in which Arc allows users to kind of have this custom experience, this special new way of interacting with the internet, is through a feature called boosts. What boosts are effectively scripts that get stored on the user's profile and executed whenever the user sort of is navigating to relevant websites, and could be on every website. So to give you an example, the really cute use case is I can have a boost that changes every typeface on every website that I go to and turns it into, Comic Sans, or turns every website into grayscale. So it's supposed to sort of like allow you to have more personal control over your experience of the web. Now, what's difficult is that Arc is meant to be consistent across your different devices. So if you're on your laptop, if you're on your mobile phone, you can log into your Arc profile and have access to all of the boosts that you've uploaded so far. Those boosts, as a result, need to be stored somewhere, and they were stored on a Firebase DB. And what's tricky is that when you uploaded your boost to your profile, there was no validation, no authorization step to prove that you were submitting a boost that was that you should be authorized to store to that profile. So in effect, you could change the user ID in the endpoint, in the call parameter to the endpoint that stores these boosts, and submit a script to another user's ID. And that script would effectively just get hosted onto their profile. They might not even be aware that that boost has been enabled for them. And that script would basically run whenever it was designed to run. And so in the most malicious way possible, you can imagine, this could be a keylogger in the background for all Arc users. So as they're going about their web experiences, all of their passwords, credentials, financial information is getting logged by some third-party malicious actor. Now, this was discovered by a researcher by the name of XYZ Eva. As soon as it was reported, the ARC team began working on this, and it was resolved within 24 hours. But it kind of gives you a sense of where a simple authorization vulnerability can have a very significant impact on a product, particularly something that is intended to be a very high trust product. Something, your browser is supposed to be the most secure, one of the most secure products in sort of your user software stack. Okay, so these are all the concrete examples. Hopefully, it gives you a sense of how these vulnerabilities come to exist, and also a little bit of their shape. Now, I'd love to kind of share with you my personal experience, kind of reporting on some of these vulnerabilities, and how different product owners have sort of described their impression of the severity level of these vulnerabilities. What's interesting is that they're not consistently considered to be negative or malicious. So there are a lot of products that actually are aware that others are interacting with their front-end APIs in a fashion that they're not supposed to, whether it's through just programmatic calls or by using effectively these types of authorization vulnerabilities to integrate with some other third-party product stack. In a way, sometimes this type of an integration format is thought of as having a shadow SDK. So you don't actually have to build backend developer tooling for third-party developers who want to integrate with your product. You kind of get the benefit of them using your front-end APIs. And at some point, if you just don't want them to, you can send a cease and desist, shut off their access, sue them, because they're breaking terms of service by interacting with your front-end APIs in this way. It's a kind of rare case, but surprising to hear some product owners respond this way when presented with some of these vulnerabilities. Now, obviously, whenever these vulnerabilities result in data leaks or access to actions that users should not have access to, particularly admin actions that can be very malicious, that's where you kind of see more responsiveness from the teams. And so you'll often see a lot of urgency, particularly for actions that result in data deletion, because that can be something that's irreversible and difficult for the product to recover from if exploited. What's kind of happening in the background at the same time is that a lot of these authorization vulnerabilities are increasingly shifting to the right end of that scale, so being exploited to more severe consequences. To give you a sense, part of this is because a lot of our front-end frameworks today have defaults that will make these front-end APIs more accessible, and sometimes developers are not aware that that accessibility it could be exploited. So on the left-hand side is a tweet, which I really appreciate. If you're developing an Next.js app and you use config default use server, you will have exported endpoints. You'll have endpoints, public-facing endpoints for all exported functions, even functions that are not called within your client device. So if you're a developer, you might think that a particular function within your app is an internal function. It's not actually used or called anywhere on your client. It's never going to be public-facing. But because you have this config set, you may actually have a malicious actor who discovers that endpoint and potentially executes a function that they otherwise should not, you would think are not supposed to access. On the right-hand side is another example. This is Theo. Some of you may be familiar with Theo from Twitter. He's a pretty well-known developer. And he had this really funny tweet that was trying to book a doctor's appointment, and the form was broken, so I spoofed it via Chrome and was able to book the appointment. Now the question is, why was that form broken? Was the office meant to be closed that day? Was your insurance actually not meant to be accepted? Is there some reason why this call was actually not meant to be made? And so a lot of the time, we think that by removing UI or front-end sort of buttons, from users, they're not going to be able to actually execute actions. But you have increasingly sophisticated actors, particularly people with a little bit of technical capability, who are able to get around it. And increasingly with the use of LLMs, they can actually kind of have the LLM walk them through the process of making this type of a call without having a ton of familiarity themselves. Okay. Hopefully I still have you all. Now what we're going to do is pretend we are script kiddies and have a lot of patience and time and an interest in finding these vulnerabilities. So what are the steps that you might execute? The first step is you actually just log in. Let's say you're trying to find these types of vulnerabilities in a web app. You log into the product, you authenticate yourself, and you open the developer tools, go to the network tab, and start just logging all the network traffic that's being made between your client and the servers. And just click around, interact with different modals, interact with different features within the product. You might think about where sensitive data or information may be accessible. So you might go into your account settings and try to see your password if it's ever sent back to you in plain text. You might try to see what it's like to edit or update your password. Is there a particular endpoint that's called to change your password? You might look for where there's sensitive data within the app, like where your social security number may appear in your user profile, navigate to that page, and basically just go through the product in ways that you think might open access to sensitive data, and simultaneously just catalog all of the network traffic that's happened between your client and the servers. In that process, you're going to find a ton of logs. It's going to be a very annoying process. But what you're going to try to do is figure out which of those network calls was responsible for the most interesting action or data that you were able to find within your interaction. So which of these endpoints returned the social security number that's actually populated on your screen, or your password, etc. Once you've kind of done this cataloging, you'll find maybe a couple of endpoints that are of particular interest to you. Next step is you just want to replay the calls that were made by your client and see if you can actually just get a valid response back from the servers. So it's a very simple process. If you're in Chrome, you can right-click on that call, copy it as a curl command, open your terminal, just dump that curl command in, press enter, and just see what response you get back. If you get a valid response, that's great. You have the correct syntax structure for that call, and it gives you the starting point for being able to edit the call to see what else you can effectively get access to. So the next step might be, okay, so this is a call that has a parameter called count20. Maybe let's edit that and call count 2000. Do I get access to a different amount of data? You might actually, before you get into the parameters, the payload of the call, you might change the authorization header. So you might actually remove the authorization token altogether and see, is that authorization token being validated anywhere on the service? Sometimes you'll find that it's not. You might actually edit the authorization token, just change a couple of characters. I found there's some products that implement authorization checks by just doing character validation. Is this like a string that fits a regex pattern? Rather than actually doing a valid check against some sort of database that checks whether that authorization token is a real token or not. Knowing that will give you a lot of latitude around how far you can push this type of an exploit. So if authorization is not validated, you might actually be able to access a lot more data than you otherwise would anticipate. And you can kind of go through and figure out how they're able to identify your particular user ID. If it's within the call payload, you might edit that, see if there's a broken object level identifier, vulnerability, etc. It's a very manual process. So just to give you a sense, just opening the Twitter app will generate those like 220 plus network logs. Going through them is an annoying, taxing process. You kind of have to be patient, and you kind of have to read through a lot of the network logs and think about a little bit of the syntax. Like reading home timeline is a likely indicator that you should maybe like spend a little bit of time scrolling through that response log before discarding it. That type of sort of like semantic analysis, like just manually reading these logs, is very taxing for a human, very difficult to also programmatically run. And it's also very difficult to sort of figure out how to programmatically edit the variables, the parameters within call payload to return sensitive data or sort of execute one of these vulnerabilities. But what's really nice is if you're a more sophisticated entity, you actually might start thinking about how you can incorporate an LLM agent into this process to help you do both the semantic analysis of which of these logs I should prioritize, and also which of these parameters should I edit and how should I edit them for valid guesses. So a really simple example is, let's say you use an LLM, you've kind of filtered through all of these logs and found that there's a particular call to an endpoint, an EHR endpoint called getScheduledList, and that returns for you the full schedule of all the practices, sort of appointments for a particular date. Now, knowing that endpoint, it's a good starting point because you have a valid call. You can kind of start to guess what are other endpoints or variations on this call that I could maybe make to the servers and see which of them could return a valid response. So if you are manually doing this, you might actually create a list of, okay, get schedule list. This is the sort of capitalization syntax that they use for their functions. Let's come up with a bunch of other variations, get claim list, get clinician list, get service list, and see if any of those endpoints are valid as well. Coming up with those guesses, obviously manual, very low hit rate, but it's a very valuable exercise to go through. On the right-hand side, it's a little bit of an easier exercise, but you kind of see the valid call payload. You can kind of start to think, are there functions that are called, for example, include resource as a parameter in this call payload that's set to true. And so resource is often in health record or medical context, it refers to a clinician. So if it's including the resource ID, maybe you can also include other variables that might be related to a particular appointment. So include social security number. That might return the patient's social security number if it's within that same profile or patient name. Other sensitive data that's maybe available through that same endpoint. Again, coming up with the syntax that might be valid is manually taxing, but an LLM can actually create a very comprehensive list for you very quickly. And all you need to do is effectively just run all of those calls to the EHR and see if any of them return a valid response. You'll get a lot of errors, a lot of 500 errors. But if you get a hit, that indicates for you that you've identified a potential vulnerability. And effectively, it's sort of a way of fuzzing these endpoints to identify if there is a particular way in which you can access data or functions that you otherwise should not have access to. Now, this isn't always done with a malicious intention. This is sort of like the alternative way of thinking about these, the individuals who might be trying to find these types of endpoint sort of boundaries are individuals who want to integrate more deeply with your product. And often it's for reasons that are to add more value both to your product and to your users. So on the left, I imagine a lot of people in this room are familiar with Plaid. Plaid is a fintech SDK that allowed fintech developers to be able to access through one API a bunch of different banks' data. So you could kind of, instead of integrating with 1,000 different local small banks to develop a finance product, you could integrate just through Plaid, and Plaid on its back end would have individual scripts written for each of these different banks and pull things like your checking balance, your how many accounts you have with a particular bank, etc. The way Plaid did this initially was by basically asking for the credentials of a particular user, and by submitting those credentials on the user's behalf through effectively screen scraping. So they would log in, simulate a browser event, and navigate effectively to the places within products where the checking account balance would be reported, pull that checking account balance, and then put it back into response to a call payload, and then send that back to the developers. Obviously, it added a lot of value. A lot of fintech products that we're familiar with now would not be possible without this type of SDK. And for Plaid to build this, they had to build unique scripts for each of these different products that integrated effectively through the front end of the products programmatically. Now, Plaid didn't necessarily execute any authorization vulnerabilities, but they were programmatically accessing front end APIs with authenticated credentials that were against the terms of service for effectively all of these banks. Over time, as they developed more, as they became more established, they negotiated direct integrations with these banks. But it kind of gives you a vision of what the value is of being able to integrate with a product without having to follow a specific schema that they've set out for you in a developer SDK. On the right-hand side are a bunch of foundation model companies and companies like Zapier that are trying to build agents or agentic workflows that effectively try to integrate with products through these front-end APIs as well. And so using LLMs to be able to navigate through which of these endpoints should I call, how effectively can I get around the process of not being limited to just the backend SDK that this product is set up for me. So sometimes you actually might think, all of this type of programmatic access might be malicious. But in a way, if your product is integrated through OpenAI and people can book, if you're kayak.com, let's say, and people can start to book, tickets and travel, whatever, through OpenAI, because OpenAI has opened up this sort of agentic workflow that integrates with your front-end APIs. It might actually be a net benefit for your product that you may not want to necessarily shut down directly. Okay, we're kind of at the end of the talk. So what can you do if you want to mitigate this type of attack surface for yourself, particularly authorization vulnerabilities that result in malicious actions like leaking data or executing actions that may be harmful to your other users? The first step is it's really important to begin by just monitoring. The easiest thing to monitor for is how many failed server calls are you getting from a particular session token or from a particular user ID's credentials. Before any of these types of vulnerabilities are discovered, users are typically submitting a ton of failed requests. They're kind of guessing at all of these different ways in which the call payloads can be manipulated. You can very quickly see if someone is either editing or trying to programmatically interact with APIs that are not meant to be used by a developer or someone in that fashion. That'll also give you a very quick sense of which endpoints or which actions people are trying to exploit or prioritizing for exploitation. So at a very foundational level, it'll give you kind of the basics or a sense of kind of your vulnerability footprint. The next step is to begin by thinking about how you can implement a testing harness or some sort of process, especially within your CI/CD process, that can identify these vulnerabilities before the product is actually pushed to production. So if you have an endpoint, it's actually really, I think, important to have some sort of a harness that takes a set of test credentials for a test user, or alternatively tries to establish some sort of authorization vulnerability within sort of the calls that are being made to that product endpoint, and see if anything valid is returned. Having something like that kind of programmatically testing these APIs before they're pushed to production allows you to at least predict the simplest of these vulnerabilities before they're made public. And And ideally, you kind of want to move to a model where you're using some version of these fuzzing agentic workflows, like a sort of LLM example that we walked through earlier, because that's kind of what your malicious actors will be moving toward using as well. So it'll kind of help you identify the full breadth of potential vulnerabilities rather than just taking a couple of examples of BOLA, where a user ID may be modified, but and you may be mitigated against that if you have just a unit test just for that, but may not be mitigating attacks against requesting instead of 20 rows, 2,000 rows of data. And then the last step is refactor. Just wherever you do have these potential vulnerabilities, begin to think about implementing authorization. Obviously, I think one really important element to think about is wherever you have incrementing integers as an identifier within your product, rethink that, because that makes these types of vulnerabilities much easier to exploit and their scope significantly more harmful. And particularly anywhere that you have global identifiers across your users that are publicly available. So for example, the claims IDs that we were looking at earlier in the first concrete example that we walked through, those claim IDs were global identifiers across all physicians' practices. So that makes it a lot easier to identify IDs related to practices that you should not have access to. Those global IDs, you want to make sure that either they are very difficult to guess, or alternatively are actually partitioned so that there's claim ID 1 is relates to a different claim than the same claim ID 1 for a different user. Hopefully that makes sense. And then the last step is you might think about actually implementing some sort of internal gateway that is a traffic control cop effectively for authorization that can both log authorization activity that's happening, but also try to have a bit more of a monolithic approach for ensuring authorization is implemented across your entire product stack. So you don't have a rogue microservice like that printer microservice that maybe is being executed and has full access to your database without having to go through authorization. There are examples of teams that have implemented this type of a model. One really good example is Uber. They've actually published some really great blog posts about their approach to this. So yeah, I haven't worked at Uber, but happy to answer questions to the degree that I can. Anyone else who's worked at Uber here, feel free to speak up. Yeah, hopefully the last element to think about, this is often poo-pooed. A lot of people will make fun of me for recommending this, but I actually think it's important to think about making semantic analysis of your public footprint a little bit harder to parse. So making something called include SSN as a parameter in a call payload makes it a lot easier for me to do a regex and look for where in this sort of call logs do I have social security numbers exposed. Obfuscating some of those parameters, thinking a little bit more about the sensitivity of how easy it is to semantically understand where sensitive data is made available will give you a little bit more protection, especially against some of the simpler sort of agentic workflows that may be implemented. But ultimately, if someone's looking for a social security number, it's not hard to find, regardless of how far you go with obfuscation. So it's not a foolproof element. With that, happy to pause for questions. Really appreciate everyone's attention. Great. I don't think we have any questions. Thank you so much.
All right, guys, that's Amir. Can we give one more round of applause for him, please? Thank you very much. Thank you so much. All right.